Good afternoon and welcome. My name is Suraj and I am a GSI for Data 100, and today we're going to be walking through discussion 11 from spring 2020. In this short video, I'll be walking through question number 1, which deals with residuals. And so question 1a asks, we fit a simple linear regression model to our data where xi is the independent variable and y is the dependent variable. Our line is of the form, y hat is equal to a hat plus b hat x. So nothing new there. Suppose we plot the relationship between the residuals of our model and the y hats and find that there is a curve. What does this tell us about the model? Okay, so I won't go answer through answer. What I'll do is just sort of give us a sense of what the question is alluding to. Okay, so what this is telling us or asking us is if we plot our residuals on the x-axis, our predicted y values on the y-axis, and notice that there is a discernible, curving relationship between the residuals and the y hats. Like, what does that mean? And this is actually the same situation that you're faced with in Lab 9 from this semester, which is the current lab if you're watching this video the week it came out, right? You saw that you just use horsepower as an independent variable, and you see that in the residuals there's a clear parabolic relationship. Okay, so taking a step back, what we ideally want in our residual plot is to see no clear relationship. Okay, so if we did a good job at fitting a model in order to predict our y hats, there should be no relationship between the residuals and the y hats. And if there is a relationship, it means that our model is not fitting closely enough to our data. And what it really means is that we need to add more features or do some sort of feature engineering to be able to better capture the underlying relationship between, our inputs and our outputs. And so that's exactly the case here, right? We see that there's this like parabolic relationship or whatever curve relationship between our residuals and our y hats. And what that means is we likely need another feature, so like a feature that's quadratic or something, added to our model in order to make the residual plot look like there isn't a pattern, which is the goal, right? We want our residual plot to not look like it has a pattern. Okay, so with that in mind, let's take a look at the answers. Right, the only answer that is really consistent with what I just said is option C. The variables need to be transformed or additional independent variables are needed. And I didn't explicitly say this, but independent variables and features are synonyms, right? We typically use features in the machine learning terminology when we talk about a design matrix and that sort of thing, and we use independent variables when we're looking at it from a statistics perspective in terms of this is our model, these are our dependent and independent variables. So option C is the only one that's really consistent with what I just said, that our model is likely not sophisticated enough to model the relationship between our inputs and our outputs. Option A is the opposite of what I just said, right? It says the relationship between our dependent and independent variables is well represented by a line. It's not well represented by a line. We need more than just a line to represent this relationship. So option A doesn't work. And option B is, to be honest, sort of just one of those options that's added in there to make you pick it if you're not sure what the option is, but it doesn't actually mean anything, or it's not really relevant to what the question is asking. So we can just ignore that as well. The point of this question was to realize why option C is the correct one and option A isn't correct. And again, to emphasize, it's because if there is some sort of pattern in your residual plot, it means your model is not sophisticated enough to handle the relationship between the inputs and the outputs. In part B, we're asked, which of the following are useful properties of residuals in an ordinary least squares regression with an intercept where the dependent and independent variables are vectors? Okay, so here we'll go option through option, but before doing that, I wanted to quickly recap the assumptions that we can make while looking at these options. So we know in ordinary least squares, what we know is that our residuals are orthogonal to the column space or the span of X, right? And I won't go exactly into why this is the case, but the theta that we choose is the one that satisfies this property. Okay, and one way to represent this relationship is that X transpose our residuals, where R is the residual vector. And we can draw a vector hat on it if we want. One way to incorporate sort of represent this fact is that if we take our design matrix X transposed with our residual vector, we get 0. And what this is really saying is that our design matrix X will contain the features in the columns, right? So each column will be one feature that we're using in our model. And so we're told we have an intercept term. So what that tells us is one of our columns will contain all ones. Our next column, let's just call it feature 1. Then we'll have so on and so forth until feature P. And this notation is similar to how you index into pandas, data frames, and matrices, right? I'm saying all rows in this column. So this is saying give me all rows and the pth column, which is just referring to the pth column or pth feature, right? What I know is that under the ordinary least squares model, each of these column vectors, right? So I have a column vector here, a column vector here, a column vector here, each of which is one feature. Each of those is orthogonal to my residual vector. Okay, so this entire matrix, if I inner product it with the residual vector, I get the 0 vector. If I take any one column on its own and dot product that with the residual vector, I will get the scalar value 0. So to be clear, this is a vector of all zeros, but if I do any one of the individual dot products, I will get the scalar 0. Okay, so the first choice is that the average of the residuals is equal to 0. Okay, and so that is true, and let's now quickly walk through why that is the case. And it has to do with the fact that we have this intercept term. Okay, if we don't have this intercept term, this property isn't necessarily true. And so, as you will see, having an intercept term will allow a lot of properties to be true that aren't necessarily true otherwise. Okay, so now that we have this intercept term, and we know that each column in our design matrix X has to be orthogonal to the residuals, meaning that their dot product has to be 0, I know that the dot product of this column of all all ones, sorry if I said all zeros, I meant all ones, the dot product of that with our residual vector has to be 0. Okay? And we know that our residual vector is just made up of a bunch of scalars, right? Residual 1, residual 2, so on and so forth, till residual n. I know that this dot product has to be 0 because they're orthogonal. Writing this out, this tells me that 1 times r1 plus 1 times r2 plus so on and so forth plus 1 times r sub n has to be 0. But all this is really saying is that the sum of all of my residuals is equal to 0, with I going from 1 to n. But if the sum of the residuals is 0, I can just multiply both sides here by 1 over n and also get that the average of the residuals is 0. Okay? So that's a direct proof of why the average of the residuals is 0 in this specific case when we have an intercept term. If we don't have an intercept term, this property in general is not guaranteed to hold true. The second option is asking us if it's true that the inner product of the fitted values and the residuals is always positive. And so remember, the fitted values is what we predict. It's our predicted y's. It's asking us if the inner product or the dot product of this with our residuals is always positive. And so the answer is that it's not. And now let's look at why that's the case. So one fact we will need is that our independent variables, so our inputs x and our residuals are orthogonal. So we will need this fact, and so I'll write that down here again. So we will need that x transpose the residuals is equal to 0. And this is a vector, but as you've probably noticed by now, sometimes we get lazy and don't write the vector hat above everything. The y hat is indeed a vector, right? So it's asking us if it's true that this dot product with the residuals is always positive. And so what we know is that our model is that y hat is equal to x times theta hat, right? We take our, this is our model. This is how it's defined, right? So I can plug in x times theta hat in for y hat, and I'm looking at the dot product of that with the residuals. A fact from linear algebra we will need is that if you have a matrix vector or matrix multiplication transposed, that's equal to the product of the transposes in the opposite order. So A times B transpose is equal to B transpose A transpose, whether B is a matrix or a vector. And we can apply that here. So we can say that this is theta hat transpose X transpose the residuals. And now what can we do? Well, now we can use this fact. The fact that X transpose the residuals is 0. So I can plug that in here and I have theta transpose, a vector containing all zeros, which is just 0, right? And really this all revolves around the fact that in the multiplication of our fitted values with the residuals, one of the factors you can say is X transpose the residuals, which is 0. And so since that 0 is contained, the entire thing is equal to 0. And so that means the inner product of the fitted values and the residuals is always equal to exactly 0. Okay, and 0 is neither positive nor negative. So neither positive nor negative. And so that's why this option is false. It's because the inner product of the fitted values and the residuals is actually always 0. Whether or not we have an intercept term, actually, because we didn't use the fact that we have an intercept term in this problem. The last option is asking whether or not it's true that the residuals and the independent variable are orthogonal. And so that's true, and that's true by this fact, right? And we've sort of been operating under that assumption since the beginning. The theta hat we choose is the one that makes our residuals orthogonal to the column space of X, which, written down in a precise statement is this exactly, that X transpose the residuals is 0. So the residuals and the independent variable are orthogonal in ordinary least squares. And that is essentially the key of part B. It's understanding, 1, that fact is true, and 2, what other properties come with that. Okay, so option C is indeed true. And then I believe that wraps up question 1 on residuals.